Today, hello guys. Today we'll be doing paper 4, February March 2021, and I think we should get started now. So the first question, it says that please wait. Okay, so this one says okay, it says sorry, let me grab my eraser. And now the first question over here, it says the most common oxidation states of cobalt are +2 and +3. All right. Complete the electronic configuration of the following free ions. Okay, now we know that the atomic number for cobalt is, can you spot cobalt over here? Okay, so cobalt is, let me see, over here it's 27, right? So what we do is we erase this, and what we do is we do you know the how we write the configurations? So it's 1s2, then it comes with 2s2, 2p6, and then 3s2, 3p6, 3d10. Alright, and then it's 4s2. So it's a 2 over here, so it's 3s2 over here. Okay, now 4p6, and then 4d10. So that's how it goes along. So now how we fill in the electrons is, first it's 1s2, then it becomes then the 2s2 is filled, then 2p6, then 3s2, and now after 3p6, 3d10 would not be filled, as 4s2 would be filled, and then 3d10, and then 4p6. Alright, so cobalt has 27, so plus 2 would be what? Plus 2 would be 25 electrons. So it's 1s2. So argon is how much? Let me see. So argon over here, it's written that it's 18. I don't know how to move this. So it's basically 18. Argon is 18, right? So what we do is we don't write about the first 18 electrons, which is 1s2, 2s2, which makes up 4, then 2p6 is 10, then 12 with 3s2, and 18 with 3p6, right? So we write what is going to come next. So 25 minus 18 would be 18 6. So 25 minus 18 would be 2 and 7, right? So what we do is we write so in cobalt, which is 27, what we do is we write 4s2 and then 3d whatever that is. But when we are removing the electrons, what we do is we remove the electrons from 4s2, and then we move on to um, the 3d10 electrons, right? So let's write the configuration for cobalt first and not the ions. So what it would be, Ar, which is 18 electrons, then it would be 18, and 4s2 would be 20, and 3d7, right? Because this would make up 27 electrons. Okay, but in CO plus 2, this one, um, 2 electrons are being lost, so these would be removed, these electrons would be removed, and it would be 3d7 only. Now in this one, 3 electrons are being removed, which means these two and one from 3d7, so it would be 3d6 and 4s0 for both. 3d6. Let's look at the marking scheme. Okay, sorry. Okay, so it's 3d6 and 4d7 over here. 3d7 and 3d6 over here. Alright, so I hope you understood. Let me erase the screen, whatever I wrote. So okay, now coming on to the next question, which says, okay, how do I move downwards? Okay, yes. Okay, over here it says CO plus 2 and CO plus 3 both form complexes with EDTA4 minus. Okay, so this is EDTA. Okay, no, let's see. Use the data in the table to predict what happens, if anything, when separate aqueous solutions of CO plus 3 and COEDTA are left to stand in the air. Okay, so what happens to CO plus 3? Let's see. So aqueous solution of CO plus 3 is are left to stand in the air. So what happens is it is reacting with oxygen, right? So CO plus 3 is reacting with this one. So the first product is this, and the second product, and the first reactant would be CO plus 3, right? So this one would be as it is, but since it is reacting with air, so the other one would be reversed, this one would be reversed. Alright, so it would be 1.82 minus 1.23. Alright, so that would be the answer. And when separate solutions of CO plus 3 are okay. So that is it, and we'll write that oxygen will be formed. Okay, so oxygen is formed, and what's the next one? Okay, so CO plus 3 is reduced to CO plus 2 since it is gaining an electron and becoming CO plus 2. Oxygen gas is evolved, and E of CO plus 3 is greater than electronic potential of O2, and that's what I said, that since this is greater and this one is lesser, so this would be reversed, right? So that is it, and oxygen would be formed. Now moving on to, let me erase this. Okay, now moving on to the aqueous solution of COEDTA. We'll follow the similar procedure we did in the earlier question. So it's COEDTA minus, that's one of the reactants, and it is left to stand in the air. What happens next? So this equation's electronic potential is lower than that of this one, right? So what we do is, so what happens is, So we react oxygen with CODTA minus 2, and okay, no, what we'll do is, since over here it's written CODTA minus, so okay, so since the electronic potential for oxygen is larger, um, oxygen would be reacted with COEDTA minus 2 to form this and water. Alright, let's look. So okay, so it's not feasible. Okay, alright, I'm so sorry. So since let me explain it to you. Okay, since over here it's written that it is the aqueous solution for COEDTA minus, we'll just say that it is not feasible because this is lower than this one. So the electronic potential would be 0.38, and we'll have to reverse this electronic potential, which would become minus 1.23, and it would be lesser than 1, so it would be negative, lesser than 0 basically. So it would be negative, and that means that the reaction is not feasible. Alright, let me erase this. Okay, now moving on to the next part. It says hydrated cobalt nitrate, this is the formula for cobalt nitrate, is a red solid, okay, that behaves like hydrated magnesium nitrate when heated. Okay, so describe in detail what you would expect to observe when crystals of cobalt nitrate are heated in a boiling tube, gently at first and then more strongly. So it behaves like the group 2 salts, and we know that group 2 salts, when they are thermally decomposed, their nitrates, what do they form? They form, so when magnesium nitrate would be magnesium nitrate would be thermally decomposed, what that would form is, let me tell you, so it's 2. I am really bad at writing with a mouse. So it forms MgO plus NO2 plus O2. Alright, so that's what forms. We don't need to balance this right now, but that's what they're asking for. So basically, what does gently at first means and then more strongly means? So thermal decomposition of this one requires much more heat as compared to gently heating it. So what gently heating that means, that first we'll evaporate the water which is present in the hydrated cobalt nitrate. So they are just crystals of cobalt nitrate, and then we would then cobalt oxide would be formed with nitrogen, and cobalt oxide would be formed. So instead of Mg it would be CO, and NO2, which is a brown gas. So a brown gas would appear, and cobalt oxide would be formed, and I am not sure what the color is, so why don't we search it up. Cobalt oxide color, I think it's black. Okay, so it's olive green or gray solid. So we write olive green or gray solid, right? let's look at the marking scheme. So it says condensation on tube, steam evolved, and that's what I said, that we'll evaporate the water. Then brown fumes of NO2. O2 form that relights a glowing splint. Okay. Solid dissolves. So over here it's written that it's a red solid, right? So we just say that it dissolves. We don't need to know the color of cobalt oxide. And we achieved the 2 marks, which was condensation on tube and brown fumes. Okay, so let's move on to the next part, which says, let me erase this first. Okay, so in the next part it says, explain why the thermal stability of the group 2 nitrates increases down the group. Okay, so in some questions they don't even tell you that it increases or decreases, and that question is for 3 marks, since we have to tell that if it increases or not. So you need to remember that it increases as well, right? So the reason is that the polarizing power of the ions increases down the group. Alright, so polarizing power increases down the group. Polarizing power increases down the group, and it's difficult, and this there are strong bonds forming between them. So a lot of energy is required to separate those bonds. Okay, let's look at the marking scheme, which says, you need to memorize this. So cationic radius increases and less polarization, so the polarization decreases. All right, you need to memorize this. I can explain it to you in the next chapter, but in the topic where we solve the where we do this chapter, but you need to memorize these 2 points. They're pretty common and they're like free marks. Okay, so cationic radius increases down the group, and less polarization, distortion of nitrate ion. Now let's move on to the next question, which is, okay, so this is a really easy question. So it says iron 2 compounds are generally only stable in neutral, non-oxidizing conditions. It is difficult to determine the lattice energy of FeO experimentally. Use data from the data booklet and this Born-Haber cycle to calculate the lattice energy, this one, of FeO in kilojoule per mole. Okay, I need to keep erasing what I have written, and it's pretty annoying. Okay, so what you do is, okay, so over here FeS plus half O2 gas forms FeO, which is in solid form. That's the enthalpy change of formation of FeO. Alright, so we write formation, enthalpy change of formation of FeO. Alright, okay, now moving on into the upward direction. So this is FeS, and over here it's Fe gas. Okay, so it means that iron is being atomized. So this is the enthalpy change of atomization of iron. So so it's enthalpy change, atomization of iron. Okay, and now over here, from this to this one, it says, so there's half O2 gas, and over here it's only one oxygen. So over here it's half and O2. So what's happening over here is that there's atomization taking place over here as well, but of oxygen. So half AT and O. Okay, but when O2 is atomized, okay, no, that's it. So let me see. So if O2 was atomized, it would have formed 2O, right? But over here it's half, so we'll multiply this by half as well. Okay, now so now in this from this equation to this equation, an ion, a cation is being formed, right? So when a cation from an atom is being formed, that's known as electronic affinity. So that's known as ionization energy, sorry. So ionization energy, first ionization energy of iron, and over here they're forming it another cation. So this was Fe plus 1 and over here it's Fe plus 2. So this is the second ionization energy, right? Now from Fe plus 2, Fe plus 2 is remaining the same. Now O gas is forming an anion, alright? So this is the first electronic affinity of oxygen, and this is the second electronic affinity of oxygen. Okay, now what do we have to do? I'm not erasing this just yet, so we have to find out this. All right, now we need to calculate the values as well. Okay, so these two values are given, and we need to find out the atomization of oxygen. So we need the data booklet for that. So we write data booklet chemistry Alevels 2022 show. Okay, so it's okay. Let's move on to the data booklet, which is pretty far. Okay, here it is. Okay, now we want the atomization of oxygen. So over here, this one, that's the atomization of oxygen, but that's the double one, right? So this would form two oxygens, but in the question there is only one oxygen, so we divide 496 by 2, which would be let me so 496 by 2 would be, let me calculate it, so it's 248. So this one would be plus 248 plus, now the first ionization energy of iron, let's see, it was over, let me see, iron over here. So sorry, so the first ionization of iron is 20, no, so the first ionization is 762 and second is 1560, so 762 and 1560. So 762 over here and 1560, sorry, 1560, the second one. And now the first electronic affinity is also given and second electronic affinity is also given. Now we just have to calculate it. So how will we do that is, so plus 416, let me write it. So plus plus 416 plus this is 248, right? So 248 plus 762 plus 1560, and this one is minus, so we write minus 141, and then plus 798, and then it's plus and x because that's unknown, right? Which is equal to what? 272, minus 272. Okay, so now let me tell you how I did that. So these arrows, as you can see, they are in the upward direction. Now this is also, this is in the same direction basically, right? So it's moving like this and then this, then this, and then this, but the next one should be like this in the upward direction, but it's not. So we put an equal to and then the one which is over here, minus 272, because in the it is not in the same cycle. So this is one cycle, right? But this one is not, so we put an equal to over there and then solve it. So what it would be is, let me see, so we add all of them. So 416 plus 248, 416 plus 248 plus 762 plus 1560 minus 141 plus 798, which becomes 3643. So 3643 plus x is equal to minus 272. Now we bring this so we bring this minus 3643 to this side, plus 3643 to this side, and it becomes negative. So minus 272 minus 3643 would be minus 3915. So it would be minus 3915 is equal to x, and that is the lattice energy. Alright, so let me check the answer. Okay, so let me erase it. So over here, do you see that it's minus 3915? So that's the answer. I hope you understood it, because it's pretty easy. Okay, now, so over here it says most naturally occurring samples of iron oxide are found as the mineral bushite. It has a formula of Fe20OX, and it contains both Fe plus 2 and Fe plus 3 ions. 90% of the iron is Fe plus 2 and 10% of the iron is Fe plus 3. Reduce the value of X. Okay. So what we do is, um, so okay. So does this have any link with the upper question? Okay, it does not. So it's just 1 mark. but how will we do it? So 90% of the iron is Fe plus 2, right? So which means that 20 of 90% would be 18, right? So 18 are Fe plus 2 and 2 are Fe plus 3. So if we calculate the, let me see. So if we calculate it by 18 multiplied by 2, which is 36, and 2 multiplied by 3, which is 6, so 36 plus 6 over 2 would be 21. So Fe would be plus 21, and that's how this x would be 21 as well. Let's see how they solved it. Okay, so they did what I did. So 0.9 into plus 2 and 0.1 is plus 3 and 20 multiplied by that. So that's what I did. So 18 into plus 2, that's the same thing, and 0.1 sorry 2 into plus 3, which is 6, minus 2x. So what I did was this was what this the answer came 36, right? So 18 into 2 plus 36, 18 into 2 is 36 and 2 into 3 is 6, and I divided this by 2. Alright, and the answer came 21, which is the charge which is this thing over here. Alright, so that's how you solve this one. Now moving on to the next question. So it says state and explain how the lattice energy. Okay, so lattice energy is dependent upon, let me tell you. So it's directly proportional to charge and inversely proportional to size. Alright, so Fe plus 2 and Ca plus 2 have the same charge, so it only depends upon the size now. Okay, so which one has a larger size? We can check it from the data booklet. Where was the data booklet? Over here. So Fe has, let me see, wait. Okay. So Fe and Ca, right? So where is calcium? I cannot find it. Okay, so Ca plus 2 is 0.099 and Fe plus 2 is 0.061. So 0.061 and 0.099. So the size of calcium is bigger. So calcium size is bigger, and the lattice energy would also be more, right? So lattice energy would be more exothermic for calcium since it has a larger ion, and vice versa for the other ion, which is Fe. So FeO more exothermic. Okay, sorry. Were we doing the okay? No, we were doing the size. So this is not the charge. It would be the opposite. So size of calcium is bigger, so this would be more, and the lattice energy for calcium would be lower. So it would be the opposite, basically. So greater attraction and stronger ionic bonds. Okay. Now let's move on to the next question. I hope you're understanding it. Okay. Now it says heating of FeO results in the formation of Fe3O4, 4FeO, which forms this. Each formula unit of Fe3O4 has contains one. Okay, this and this. Okay. Show how reaction 1 can be described as a disproportionation reaction. So what disproportionation reaction is that one ion is gaining an electron, and basically it is being oxidized and reduced in the same equation. So this one FeO is plus 2, right? And so the oxidation states, and this iron alone is an atom. It is not combined with anything, so it is 0 over here. But this one has both Fe plus 2 and Fe plus 3 ions, which means that the oxidation state from this to this is being decreased, and from Fe plus 2 and plus 3 it is being increased. So that means that it is being oxidized and reduced at the same time, and that's what the answer is. Let's check the marking scheme. So yes, that's it. Fe plus 2 reduced to Fe, and so yes, that's it. It is being reduced and oxidized at the same time. Now let's move on to the next question, which is next part, basically. We'll only be doing 2 questions right now, and we'll do the rest in the next class, which is tomorrow. Okay. So Fe3O4, how many parts are left for this question? Okay, it's pretty long. Okay, no, only 2 pages basically. Okay. So it says Fe3O4 can be electrolyzed using inert electrodes to form Fe. Write the half equation for the reaction that occurs at the anode during the electrolysis of Fe3O4. So at anode, oxidation takes place. Alright, and we have to write the half equation for the reaction, okay, to form Fe, right? So let's look at the data booklet and write the oxidation equation for Fe. So where do we find Fe? Let me see. So one is Fe plus 3 to Fe plus 2. Okay, and do we find any other? Let's see. Nope, over here. So there are 3 equations over here, right? So now let's see what they're asking for. Can be electrolyzed using inert electrode. Okay, so let me read the question if there's anything written. So Fe3O4 has both Fe+2 and +3 ions, but we need to see that which one is being oxidized. So Fe+2 to +3 would be oxidation, right? Okay, no. So write the half equation for the reaction that occurs at the anode during the electrolysis of Fe3O4. Okay, so it's Fe plus 3 and O minus 2, or this could be plus 2 as well. So oxygen would be formed at the anode because oxidation is taking place at that end. Alright, so we'll write this equation. O2 O2 minus gives us oxygen and 4 electrons. Now it says calculate the maximum mass of iron metal formed when Fe3O4 is electrolyzed for 6 hours using a current of 50 amperes. Okay, so the first formula would be Q is equal to I T, and we have to find the maximum mass of iron formed. Okay, so Q would be, I don't know, so Q we have to find out. I is 50 and time is to be written in seconds, which would be 6 hours. So 1 hour is 3600 seconds. So 3600 multiplied by 6 would be 21,600. Okay, so 21,600 multiplied by 50, it is 1 2 3 4 5 6. So 1.08 into 10 raised to power 6 coulombs. Okay, now we know that 1 Faraday is 96,500 coulombs, and we know the formula F is equal to LE, right? So now Okay, over here it says LiFePO4 can be used to lithium and lithium ion rechargeable. Okay, share one possible advantage of developing cells such as lithium ion rechargeable batteries. So they don't cause pollution. It's a guess. You need to check. Okay, so it's small size, compact, low mass, high voltage. Okay. Now over here it says use the cathode half equation to determine the change, if any, in oxidation states of lithium and iron at the cathode during discharge. Okay. So change in oxidation state during discharging. So it's for a cathode, right? So lithium, let's find out the oxidation states. So PO4 is -3. So let's consider this as -3, and this is +1 to so this is PO4 -3, and this should be Fe +3, right? So this would be +3, and I think this would be +3 to +2, and if Li would be +1. Yes, +3 to +2 and +1 to +1. So no change in lithium, and iron changes. Okay. Write the equation for the overall reaction that occurs when the cell is discharging. Okay. So this is cancelled out. This is cancelled out. So it becomes FePO4 plus LiC6 gives us 6C and LiFePO4. Yes, that is it. Alright. So I hope you understood till here, and that is it for today. We'll be doing the rest of the questions later on. Bye bye.